Has anyone seen Nina? She's supposed to be helping out with our Time of Your Life exhibit, but I don't know where she's gone. Perhaps she's left us some sort of a clue. Oh, that's really cryptic. Let's try again. No, that's not much help either. Where is she?
I'm in here.
Where?
In here.
What are you doing in there?
I wanted to get inside my head.
Why?
To see what it feels like.
And what does it feel like, Nina?
Well, to be honest, it's pretty hot in here.
Well, why didn't you come out then? We've got work to do.
Okay, I'll see what I can do. I need some intro music though. Oh, that's better. That's better. I can see everyone now. Hello. Hello. Right. This entire talk is an experiment, which means anything could happen, okay? You're going to be providing some of the data, so what we get out of this kind of depends on what you put in, okay? Right. So, like every good experiment, we're going to start with a really simple question. What is the temperature of your brain? And you might be thinking, this is our most important organ. Surely we know this already. So let's have a vote. We're going to go old school, so I just want you to stick your hands up, okay? Who thinks 36 degrees? Anyone? Oh, a couple of takers. Okay, lovely. How about 37? Okay, lovely. What about 40? Oh, you've been reading my paper. Thank you very much. Okay. Well, the good news is you are all correct at least some of the time. But how do we know this? How can we actually measure brain temperature? Well, if you're unlucky enough to have suffered a serious head injury, you might end up with one of these probes in your brain. And it measures lots and lots of things, but it can also measure temperature. Now, the great thing about these probes is that we're directly measuring the temperature of brain tissue continuously around the clock. But there are some downsides. So first of all, we can only collect data from one tiny part of the brain, okay? And these probes can only be used in brains that are already injured. And we know that injury affects temperature. So we might not be getting the same values as a normal, healthy brain. So we need to choose the best method to answer our research question. Now, I've said brain probes give us true values, but we can't stick them into healthy brains, okay? During the pandemic, you may have had one of these pointed at your forehead. This infrared thermometer measures the temperature of your skin, and then it uses clever maths to figure out what your body temperature is. It doesn't measure brain temperature. The digital thermometers that you stick under your tongue or in your armpit, they can only measure what they touch, and it's not the brain. So how are we going to measure multiple regions of the healthy brain without damaging it? Well, we can use a brain scanner or an MRI machine. Brilliant. Okay, now all we need to do is turn an MRI scanner into a thermometer. How on earth are we going to do that? Well, it all boils down to the most important molecule in life, good old water, or H2O. Now, any element with an odd number of protons in its nucleus acts like a little magnet and can be used for magnetic resonance studies. Hydrogen is perfect because it's the most common element in the body since we're mostly made of water. Okay, so to demonstrate how this works, I'm going to need up to about 10 volunteers. Now, I should say that if you volunteer, you are giving your consent to be recorded, but I promise I won't make you do anything embarrassing. And there will be a prize. So, Jack's going to show you what you could win if you volunteer. What can they win, Jack?
Yes, indeed. You can be the proud owner of one of these brain-shaped cookie cutters. You can impress all of your friends, all of your dinner guests with brain-shaped cookies cut in this orientation or this orientation, but not this orientation and not this orientation.
Okay, we want to really sell it to them, Jack, so let's have some background music. Yeah, work it, Jack. Excellent. Oh,
Seeing
yeah, okay.
hands.
We need some, okay, let's have everyone volunteering. Can you come over to here? Oh, yes, come on down, yes. Lovely, we'll have some little people. Let's have some, whoa, okay.
We only have 10 of these.
Okay. Whoa, okay, right. We may run out of cookie cutters. Okay, this is good, this is brilliant, lovely, perfect, thank you. Everyone else, thank you so much, but take a seat. Wow. Okay, we're going to need more cookie cutters. That's fine.
We will post them to you if you don't get one today.
Fantastic, fabulous, thank you so much. Right, I want you to sort of slightly shift over to that side. Brilliant, perfect, looking great. Awesome, thank you so much. Okay, right, that's just so everybody can see the slides. Okay, so I want you all to imagine, okay, that you are hydrogen protons in brain tissue, and this brain is inside an MRI scanner, which is basically a giant magnet, okay? Now, we haven't switched the magnet on yet, but when we do, the direction of the strong magnetic field will be upwards towards the ceiling, okay? Now, hydrogen protons normally spin around on their axes, generating their own magnetic charges, which are randomly oriented. So I want all of you to start spinning round on the spot. Brilliant, lovely, okay. And because you're all randomly oriented, I want all the girls to put their hands in the air up to the ceiling and all the boys to point down to the floor. And if you don't know, you can just point wherever you like. Keep spinning, lovely, fantastic, lovely. Okay, good, so we're all spinning protons. Now, we're going to turn on the big magnet, and all of you are going to point your arms upwards in line with the main magnetic field, up to the ceiling. Brilliant, lovely. Okay, now within this strong magnet, the protons also wobble a bit, like spinning tops. So give me a wobble, a bit like this. Brilliant, fabulous. So we can wobble like that, and hopefully, and now, the frequency or the speed of this wobble is important to what happens next because we're going to apply some radio waves, and today we're just going to use some music. So let's go with some music. Bit of wobbling. Lovely. In time with the music. Fabulous. Bit of spinning as well. Bit of spinning, all points to the sea. Lovely. We love that. Okay. Very good. Very, very good. Okay. Now, we've gone too far. Try to go back, which we can't do. Okay, well, if the resonance and if the waves are applied at exactly the right frequency as when you like to wobble and spin, what happens is you get really excited and you wobble some more, a bit more vigorously. Okay, and we've turned the music off and we've turned the radio frequency waves off. And then what's going to happen is you'll all just fall back gradually as to how you were into your randomly oriented spaces, and your arms are going to fall. Yeah, that's good. Brilliant. Okay. And then what happens is that the MRI scanner detects the energy that's released when all of that falls back to normal. And that is how we measure the brain. We can measure the structure of the brain in that way, and that is what's called magnetic resonance imaging. So this tells us about what the brain looks like, okay? You can see the brain there, and this we can use to decide where we're going to measure brain temperature. So we've maybe picked a little square in the middle, so we might pick there, we might pick anywhere we like. So that's going to tell us, MRI, what the brain looks like. But We want to know what the temperature is. So to measure the temperature in each part of the brain, we use this very special technique called magnetic resonance spectroscopy, or MRS. This measures the chemical composition of the brain tissue and the resonant frequency of protons in water, like you guys are. We're all really, really energetic, and you're very, very sensitive to temperature changes, and the resonance of a reference metabolite, not sensitive to temperature. So we can use the difference between the water protons and the reference protons to get an estimate of what the exact temperature is. Okay, so that's how we're going to do it. That's how we're going to turn an MRI scanner into a thermometer. And didn't they do well under lots of chaos and miscoordination? But thank you so much, everyone. Please go and collect your prize from Jack and take a seat. Everyone give him a round of applause. Fabulous. Don't worry, we will get more cookie cutters. Yes, there'll be more cookie cutters, I promise. But you all did fabulously well. Oh, we've got an extra one, an extra runaway proton. Brilliant, fantastic. Runaway, okay. Good job. So we'll take your seats. Brilliant, lovely, well done. You can spoil all your friends with brain-shaped cookies. You can find where you were. Okay, we promise we will get more cookies, and if you go to Jack afterwards, he's going to bet his mortgage on more cookie cutters. Lovely. Okay. Brilliant. Fabulous, thank you. Okay, so now we know how to measure brain temperature, right? Fabulous. Okay. We have now got the perfect method to get a 3D map of human brain temperature. We can design our experiment with healthy volunteers. Now, because body temperature has been well studied in humans, we used published body temperature data to make some predictions about how brain temperature might vary. So first of all, you may have noticed your fingers are colder than your gut. The laws of physics predict that temperature at the core of a living thing is going to be hotter than at the surface, okay? So we predicted that the center of the brain would be hottest, and we wanted to measure different parts of the brain. Second of all, we know that females tend to be warmer than males, okay? Especially in the post-ovulation phase of their menstrual cycle. So we included both sexes, and we also checked what stage of the menstrual cycle the females were in when we scanned them. Now, like all other mammals, we regulate our body temperature, and as we age, our regulation of our body temperature doesn't work so well, and also our temperature might vary if we're not well or if we've got an infection or something. So we only included people that were 20 to 40 years old and that were healthy, okay, not having any infections. And finally, if you've been downstairs to our time of your life exhibit, you will know that body temperature varies by time of day, as determined by our body clock. And we wanted to know if this was also the case for the brain. Okay, so what we did was we scanned people in the morning, the afternoon, and the evening of a single day at fixed times. Okay, logistically complicated. But if you're interested in the body clock, you know that there are different chronotypes. Hopefully you've seen that downstairs. This means that the internal body clock aligns differently with the day-night cycle in a morning lark compared with a night owl. And here you can see the daily body temperature rhythm of two such individuals, how it aligns with external time. It's shifted with respect to each other, okay? At any given point in time, the biological clock of these two people will be at very different points in the cycle. Now, if we were to take an average of temperatures at each of these time points in each scanning session, the extent of daily variation in temperature is reduced. And if we were to average across many people with lots of different chronotypes, we might not be able to tell whether there's a time of day difference in brain temperature at all. So we use daily activity monitors on the wrist to chronotype our volunteers so that we could determine the biological time at which we were scanning each individual in each scanning session. Now, we scanned 40 healthy adults with equal numbers of males and females and brains originating from at least 5 continents. Okay, exciting brains. And now for the results, we found that normal human brain temperature is higher than expected, and it varies by brain region. The hottest part is right in the center in a region called the thalamus. Very important for sleep, very important for consciousness. Okay. So, at any given point in time, there was almost a 2.5 degree difference between the hottest and coolest parts of the brain. The brain temperature of our post-ovulation females was 0.8 degrees higher, depending on brain region. And remarkably, our oldest brains were up to 0.6 degrees hotter, suggesting that brain temperature increases between 20 and 40 years of age. And finally, we found a time of day difference with nearly a whole degree drop by bedtime in the deep brain regions. And from our healthy data, we built HeatWave. This is the first 4D map of human brain temperature. And here's a loop of temperature variations in post-ovulation females versus males. In both cases, you'll see a drop in temperature at night as predicted and as expected during sleep, and as we see in body temperature rhythms as well. Now let's see if we can get a human heat wave going in here. I want you to raise your hands in the air when you see the temperature going up, and I want you to lower them again when the temperature goes down. And we're going to add in some music as well, of course. So here we go. Nice. Let's see if we can get some coordination going. Yes, yes, very good. And down again, lovely. Keep going. Yes. 24-hour rhythms in brain temperature, lovely. Perfect. Lovely job, okay. So, we've called our fabulous map Heat Wave, and if you would like to explore it for yourself in lots of different dimensions, you can go to this QR code, and it's free to access anywhere in the world, anytime you want. Okay. So, across all of our volunteers and time points, healthy brain temperature ranged from 36.1 to 40.9 degrees Celsius. Quite hot, okay? Now, this really matters to patients because it's generally assumed that injured brains are hot, and doctors sometimes cool patients down based on seeing numbers at the upper end of that range, okay? So we gathered as much data as we could from patients across Europe who'd had their brain temperature measured directly with one of those brain probes I showed you before. And here's a summary of those data. Firstly, you can see that the temperature range was much wider than our healthy volunteers. So injured brains might be hotter or colder than normal. And it's not the case that all injured brains are too hot. And hot injured brains are not necessarily hot all of the time. Now, we tested whether any features of brain temperature could help us predict survival in intensive care. The maximum, the minimum, the range of brain temperature, these were not good predictors. However, strikingly, only a quarter of our brain-injured patients displayed a daily rhythm in brain temperature, and a lack of this rhythm increased the odds of death by 21-fold. Okay, that's an astonishing effect size. Even more astonishing is that parts of our healthy brain are hitting the peak of last year's heat wave on a daily basis. Imagine that. Pretty hot. Now, that has huge implications for understanding how the brain works because all brain cell functions are temperature sensitive. How can we hope to fix this beautiful machine of ours if we don't know the normal conditions under which it operates? That's why our study was so important. Okay? And I'm not just talking about the brain as a whole or the billions of cells it's made of, but also right down to the molecular machines that keep those cells working. And if you caught Sophia's talk this morning, you will have heard about the proteins that build up in the brain in Alzheimer's disease. I've looked at these proteins in human brain cells in the lab, and I can tell you that the way they behave and how they become modified is highly temperature sensitive. So, overall, we think that daily rhythmic brain temperature variation, not absolute brain temperature, is one way in which human brain function may be distinguished from its dysfunction. This could be a useful indicator of which patients in intensive care are going to do well and which ones might have a poorer prognosis. And disrupted brain temperature rhythms might also be an early indicator of chronic brain disorders such as dementia and mental illness, but we need more studies to test those ideas. What we really do need is a cheaper and more practical way of measuring brain temperature around the clock, and that's going to take a while to engineer. So, what can we do in the meantime? Well, I can use the data we've collected from human brains and grow human brain cells in the lab at normal human brain temperatures. It is now possible to turn human stem cells into neurons in just a couple of weeks. And like all other cells in the body, your brain cells each contain a daily molecular clock of their own, and they keep time even when they're completely disconnected from the rest of your body. I can edit the genomes of these cells so that their daily circadian clock glows, which means we can track the ticking of these clocks in human brain cells in real time. And working with other cell types, we know that temperature shifts can reset circadian rhythms. So now we can ask how normal brain temperature variation affects these clocks. First of all, from 32 degrees all the way up to 40 degrees Celsius, temperature does not affect the speed of these clocks. They still tick roughly with a 24-hour rhythm. And nothing's advancing anymore. It's okay. So, there we go. Right, but a temperature shift within the normal brain range can actually reset these clocks. And collaborating with the Lancaster lab, I've used our clock reporter stem cells to grow mini brain tissues in the lab, and we call these cerebral organoids. And here they are, glowing with their 24-hour rhythms sped up in real time. These are real human brain clocks glowing, okay, with 24-hour rhythms. If we measure how much these glow over time at constant temperature, we see a lovely daily rhythm. And now if we use a strong timing cue, we can reset the clocks in different organoids to different times so that they're all out of sync with each other. And if we then apply our daily brain temperature cycles, we can force them all to synchronize with each other again. And this tells us something really important. It tells us that daily brain temperature cycles are sufficient to reset mini brain tissue clocks. Why should we care about this? Why should you care about this? Well, it's quite possible that our daily rhythm in brain temperature is important to its daily function, including how well we learn and how well we sleep. If we disrupt our daily rhythms, as might happen in shift work or jet lag, this is likely to impact our brain temperature rhythms and therefore also our brain cell clocks. We know that daily body temperature rhythms are often disrupted very early in chronic brain disorders like Alzheimer's disease, but we don't yet know if changes in brain temperature are involved in the development of these disorders, and that's something I will explore in the future. So, what have we learned today? The healthy human brain is hotter than we thought, and this could transform our understanding of how the brain works. Many things influence healthy brain temperature in time and space, so we need to be careful about how we interpret snapshot values from patients in the clinic. And finally, healthy brains have a daily heat wave, and this might be an important sign of brain health, but we need to do more research to be sure of this. Finally, I have shown you how much brain temperature varies, but I've not really explained why. And if there's a daily rhythm in brain temperature, what goes up has to come down again. Our brain is active all the time. It consumes a lot of energy. It's easy to imagine why it's hot. But how on earth might we cool the brain down? How do we cool down this brain machine on a daily basis? Does anyone have any ideas of how we might do that? Aha! Yes, shout out.
Reset the brain clock.
We could reset the brain clock. That's one interesting idea. I like that. Well, yeah. Put it in a freezer. Say that again. Eat ice cream. Oh, yeah. Brain freeze. Yes. Oh, that could totally do it. Thing is, though, if we ate ice cream every single day, we'd have to make sure we ate it at the right time. And that gets a bit tricky. But I like the idea of eating ice cream every day. That's a great suggestion. Okay. Right. So, actually, we can just speculate for now. But because we know that blood flow is key to the transfer of brain heat, the variation we've seen is well explained by changes in blood flow in different brain regions and at different times of the day. So, it's also possible that age-related changes in the brain's blood cooling system might explain why brain temperature goes up as we age, but we do need to have more direct evidence of this, and that's something that we'll again be looking at in the future. So for now, what we can do is think about the best cooling system that we currently know we have, and that is our blood vessels, which hopefully, if the lights go down upstairs, you'll be able to see. Maybe. We see some flashing blood vessels over here? Yes. Pulsing away. So as your blood flow changes to your brain on a daily basis, this is helping to cool your brain down. Okay, very, very good. Okay, so we think it's to do with blood vessels, and now I have no hands. There we go. Somewhere in here there's a hole. Oh dear, we could be here a while. Yeah, I think I'm stuck now. There we go. Okay, lovely. So we've got some blood vessels. They pulse away, and they help keep our brain cool on a daily basis. Brilliant. You've all been a fabulous audience amongst all the chaos of today, and I would like to invite any questions from the audience. I can see there's an eager beaver already with a hand straight up. Lovely.